Problem statement. Suppose we have following three bags containing red and yellow balls. Bag 1, it has 2 red ball and 3 yellow ball. This one right here. Bag 2, it has 3 red balls and 2 yellow balls. This one right here. And bag 3, it has 1 red ball and 4 yellow balls. This one right here. If a ball is randomly selected from a random bag, what is the probability, the chance that the ball is red? These types of questions are answered by using the law of total probability. This session is about law of total probability. By the way, the answer for this is 6 over 15. Now let's look at the definition of law of total probability. Suppose we have set of events a1, a2 up to an that forms the partition of your sample space. In other words, this a1 to an, they are all mutually exclusive and they cover all possibilities. And also suppose that b is any event in your sample space. Let's understand this statement through this Venn diagram. My a1 is this one right here, my a2 is this one, and a3 is this one all the way up to my an. All my A1, A2, A3, they're all disjoint subsets. And when I combine my A1 with A2 with A3 all the way to AN, they will give me my complete sample space. That's what the word partition means. Now, B, which is this right here, it is any event in your sample space. Now, this B, it may or may not overlap with your A1, A2, A3, or AN. Then I can write my B. My B can be written as A1 intersection B, which would be this part, right? This is my B, combining with union A2 intersection B, that would be this part right here. Okay, combining with, in other words, union A3 intersection B, that would be this part. Okay, and I can keep going like this all the way to the last term, AN intersection B, that would be this part. So this is my complete B. Now the property of B is given by the property of A1 intersection B. This term union gets turned into plus, and plus property of A2 intersection B plus this union gets turned into plus property of A3 intersection B plus this union also gets turned into plus, and so on all the way to the last term, which will be property of AN intersection B. Now I can rewrite this term using conditional probability. So this is equal to probability of B given that A1 has taken place multiply by probability of A1. So this is my probability of A1 intersection B. Likewise, I can find out my probability of A2 intersection B using my conditional probability. Same thing with my probability of A3 intersection B all the way up to the last term. Now this right here is my final expression for my law of total probability. Now in literature, you will find this to be sometimes rewritten like this because it's using sigma notation, a summation notation. Now, why do we even need law of total probability? Because sometimes we are given conditional probability, this one right here, and not this term. So we are not given this term, and because we are given these terms, then we use law of total probability. Suppose 1% of the people have certain disease. In other words, probability of disease is equal to 0.01. Also, a test, it detects the disease correctly 99% of the time. What it means is the probability of test being positive given that a person has the disease is 0.99. Also, the test, it gives a false positive 2% of the time. That's also given to you. In other words, the probability that the test is going to be positive given that the person does not have the disease is 0.02. Question is this: what is the probability that a given test result is positive? Here, your D is an event that the person has the disease. DC is the complementary event that the person does not have the disease. So my D and DC, they partition the sample space. So this is my sample space right here, and this would be my D, and my DC would be this region right here. Now we can apply the law of total probability. So we can apply this equation now. And in this case, our D, that would be my A1, and my DC, that would be my A2. And my positive in this case would be B right here. So using the equation, probability of positive is given by the probability of positive intersection D, that would be probability of this region, plus probability of this region, probability of positive intersection DC. All right. Now, I know this. From here, I can actually use conditional probability for each one of these terms. So the first term will give me this expression from conditional probability, and the same thing with the second expression right here. Substitute your values, and your answer will come out to be 0.0297. Let S be the event that email is a spam, and also let W be the event that the email contains the word when in it. So the probability of S that an email is spam is 0.3. In other words, 30% of emails are spam. That's given to you. And also given to you is that probability of W given that S is equal to 0.8. In other words, 80% of the spam emails contain the word when in it. Probability of W given that S complement is equal to 0.1. In other words, 10% of your non-spam emails, they contain the word when in it. So find PW, that is the probability that an email contains the word when in it. Now here my S and S complementary, they partition the sample space. So this is my S, and whatever is not part of my S is my part of my complementary S right here. Now we can apply the law of total probability to determine the probability that the email contains the word when in it. So this would be this region right here. So the probability of this W would be given by the probability of W intersection S. That would be probability of this area right here, or probability of this region, plus the probability of W intersection SC. That would be the probability of this region right here. And now I can apply this formula directly if I want. So this in this case would be my A1, this would be my A2, and my W would be my B. So using conditional probability, I can rewrite this expression like this. I can also rewrite this expression like this. Substitute your values in there. This is given to me as 0.8 right here, 0.8. This is given to me probability of spam. That's given to me as 0.3, 0.3. And also given to me is the probability of W given that SC is 0.1, 0.1, 0.1, and also probability of SC, that's going to be 0.7. If probability of S is 0.3, then the probability of SC as complementary would be 1 minus 0.3. This will be 0.7. Solving this expression, the answer is 0.31. Suppose we have following three bags containing red and yellow balls. The bag 1 contains 2 red balls and 3 yellow balls, which is this one right here. Bag 2, it contains 3 red balls and 2 yellow balls. That would be this bag right here. And bag 3 contains 1 red ball and 4 yellow balls. That would be this bag right here. If a ball is randomly selected from a random bag, what is the chance or the probability that the ball is going to be red? Let A1 be the event that the ball is selected from bag 1. Let A2 be the event that the ball selected is from bag 2, and let A3 be the event that the ball selected is from bag 3. And also let R be the event that the ball selected is a red ball. Now, since we know the red ball has to come from one of these bags, so A1, A2, A3, they form a partition of your sample space. Let's represent this through a Venn diagram. So if this is my sample space, my A1, A2, A3, they partition it, and my red, my R, it actually overlaps with my A1, A2, A3. So the probability of R in this case is going to be the probability of your A1 intersection R right here. In other words, the probability that your red ball came from bag 1, which is this right here, plus this expression, which is probability of A2 intersection R, which means probability that your red ball came from bag 2, that would be this right here, plus probability of A3 intersection R, mean the probability that your red ball came from bag 3. That would be this region right here. Okay, then I substitute, I use my conditional probability formula to actually rewrite this expression this way. Okay, so I get this term. I also rewrite this expression using conditional probability. I get this term, and same thing with this term right here. Now, this is a lot easy to solve. I know my PA1. PA1 means the probability of selecting a ball from bag 1. Well, that's 1 over 3 because there are 3 bags in total. So probability of selecting a ball from bag 1 is 1 over 3. Probability of selecting a ball from bag 2 is 1 over 3. And probability of selecting a ball from bag 3 is 1 over 3 because there are total 3 bags. So I know my PA1 is 1 over 3. I know my PA2 is 1 over 3. And I know my PA3 is 1 over 3. All right, now let's focus on PR given that A1. This one means probability of selecting a red ball given that your A1 is true. In other words, probability of selecting a red balls from bag 1. Now, what is the probability of selecting a red ball from bag 1? Well, if you look over here, there are only 2 red balls and there are total of 5 red balls. So the probability of selecting a red ball from bag 1 is 2 over 5. And this is how I come with 2 over 5 right here. Let's look at this one. Probability of selecting a red ball from bag 2. Well, this is my bag 2. How many red balls I have? I have 3 red balls. And how many totals I have? 5. So the probability of selecting a red ball from bag 2 is 3 over 5. This is how I come with 3 over 5. Same thing with this expression right here. Probability of selecting a red ball from A3, from bag 3 is 1 over 5 because there is only one ball in the bag of total that contains 5 balls. So it's 1 over 5. Okay, substitute your values in there, solve the expression, and the answer is 6 over 15. That's the probability of selecting a red ball from one of these bags. You can also verify this in a different way. You can see that, let me just remove everything. So you can see that the probability of selecting a red ball is given by the total number of balls. How many balls you have total in this case? 15. This one has 5, 5, 5. Total 15 balls. And how many red balls you have total? You have 2 over here, you have 3 over here, and you have 1 over here. So 2 plus 3 plus 1 is 6. So it's 6 over 15. So it's kind of nice to see and verify that your law of total probability works. You can do the same problem in multiple ways. Suppose a person can commute to work in 3 different ways depending on the weather. Well, the weather can be sunny day, it could be rainy day, or it could be a snowy day represented by W1, W2, and W3. Assume exactly one type of weather must occur each day. And these are my events, and these are the probability of those events, and these are the probability of being late given that these events happen. So let's understand this. Let's look at this one right here, what exactly this means. It means that my event is rainy and the probability of getting a rainy is 0.3 and the probability of being late when it's rainy is 0.4. Find the total probability of being late. Now, these 3 events, W1, W2, and W3, they form a partition of your sample space because they exactly one type of weather condition it must occur each day. So we can apply our law of total probability. So probability of being late is going to be equal to probability of late, and it was weather 1. That would be this region. So probability of late, and it was weather 1 plus probability of being late when it was weather 2. That would be this region. Probability of late, and it was weather 2 plus probability of being late, and it was weather 3 plus probability of being late, and it was weather 3. And now you can apply conditional probability to this one, to this one, and to this one, and you will get these expressions right here. So this is my first one right here, this is my second one, and this is my third one. Now you can substitute your values. You know the probability of late, given that W1, given that it's a sunny day, is 0.1. That's given to you right here. Probability of late, given that W1 is 0.1, given to you right here. Probability of W1, which is sunny weather is zero point 0.6 given to you right here. Same thing with probability of late, given that W2 is given to you right here. So all these values are given, just plug in the numbers in there and your answer will come out to be 0.25. So there's a 25% chance that the person will be late overall considering all weather conditions.